This is Dr. Anthony Revis, and this is SVSU General Chemistry 111, Chapter 11, Solutions and Colloids. This is a one lecture only survey of Chapter 11, Solutions and Colloids. In this chapter, we will review the dissolution process, electrolytes, and solubility. Let's begin with some definitions about solutions. A solution is a homogeneous mixture of two or more substances. It's very important to note when we talk about solution, we're talking about homogeneous mixtures. In other words, there is a material that dissolves in another material and it creates a homogeneous solution. Within a solution, the solute is the substance present in the smaller amount. Whatever the smaller amount, that's a solute. The solvent is the substance present in the larger amount. So, when you take a look at a formulation for a solution that's homogeneous, the part that dissolves in is a solute. The part that receives the smaller quantity in which the component is dissolved is a solvent. So the largest part of it is a solvent, the smallest part is a solute. That's the key. Okay? So we have a solution made up of a solute and a solvent. That's the key principle. We show you some examples of solution types in this table. We have component 1 is a gas, component 2 is a gas. The state of the resulting solution is a gas. An example of that is air. Air is about 78% nitrogen, about 21% oxygen, then another 1% of other materials including carbon dioxide, argon, and a few other gases. You have component 1 is a gas and component 2 is a liquid. The solution is a liquid solution. Soda water, pop, is carbon dioxide in flavored water. And in fact, if you think of a pop, you have carbon dioxide dissolved in sugar water with a flavor color. If you have gas solid, then the solid solution. Hydrogen gas in palladium. And that hydrogen gas in palladium is often used as a catalyst. You have liquid, which creates a liquid solution. Ethanol in water. Then you can have a solid liquid, which creates a liquid, which is sodium chloride in water, salt water. And then you can have solid, which is solid. You have brass like copper, zinc, which is brass, in the solder, which is tin and lead. Okay, so these are different types of solutions. Okay, so if you notice the component 2, whatever component 2 is, which is typically the solvent, then that is the dominant phase, which gives you the state of the resulting solution. So be aware of that the dominant phase is how the solution is defined. When we talk about formation of a solution, there are 3 types of interactions in the solution process. There is the solvent-solvent interaction. So those are the intermolecular forces involved in the solvent. And then you have the solute-solute interaction. In other words, those would be the intermolecular forces between the solute-solute molecules. And then you have the solvent-solute interaction, which involves the intermolecular forces between the solvent molecules and the solute. So there are these intermolecular forces, which we've already studied, that you have to take into consideration when we talk about a solution. So let's take a look at kind of the overall view or a picture of what this looks like. And we'll start on the left side of this diagram where you have the solvent. And again, the solvent is the dominant phase. That's the largest quantity. Then you go to the far right, we have a solute, which is the smaller quantity. What happens is these two materials, they meet somewhere during the process, and we look at step 1. We have a delta H there. We had a heat involved in this process. We also have a heat value involved in step 2 and step 3. And so we can summarize these to get an idea of how much energy is involved in preparing this solution. So we have delta H in the first step is where the solvent molecules essentially must separate in order to receive the solvent. And the solution also helps the solvent dissolve or separate so that it can be incorporated within the solvent. In other words, the intermolecular forces between the solvent and the solute must find a place where they're compatible, where the solvent will then surround the molecules of the solvent to make it into a solution. And that leads us to step 3 in the process. And so we get to step 3 in the process, which is formation of the final solution. And so each of these steps has a delta H, has an energy, and we've already studied delta H and heat. And so we can sum these. Delta H1 plus 2 plus 3 gives us the delta H of formation of the solution. And this occurs because of the intermolecular forces involved in the solvent and the solute finding a way to be compatible, which means that the solvent must have some intermolecular forces that will mix or form an interaction with the solute that creates a homogeneous solution. So when we talk about solutions, we are talking about, for the most part, in this section, homogeneous solutions. So that's how homogeneous solutions are formed. The intermolecular forces between the solvent and the solute find some area where they are both compatible to form this homogeneous solution, and you can calculate the values for that solution formation. So what can we say about this solvent-solute interactions? What can we say about the intermolecular forces involved? There is a golden rule for solubility, and it's this: like dissolves like. I like to say like likes like. Get it? So like dissolves like, or like likes like. If they're alike, they'll probably dissolve each other. If they're not alike, they probably won't dissolve each other, or won't dissolve in the solvent. So if the solute is more like the solvent, it will dissolve in the solvent. If the solute is not like the solvent, it might not dissolve it. Okay? So if two substances have very similar intermolecular forces, then they are likely to be soluble in one another. Not always the case, but it's highly likely. That is the starting point for trying to find a solvent that will accommodate a solute. Okay? So it works like this. Nonpolar solvents dissolve nonpolar solutes. That's the general rule. And that general rule will hold for most of the materials that you will encounter in freshman chemistry. Polar solvents dissolve polar solutes, and polar solvents also dissolve many ionic solvents. We've talked about the interaction of water, for example, with cations, and water with anions, and with other ionic species. And because of those interactions, and we're using water as an example, it happens for other solvents as well. But in the case of water, it now allows those ions to be dissolved or enter into the water phase. And when it enters into the water phase, it forms a solution. It does likewise in other solvents. So, nonpolar molecules are soluble in nonpolar solvents. So if we have carbon tetrachloride in hexane, then we expect it to be soluble. In other words, we expect nonpolar carbon tetrachloride to be soluble in nonpolar hexane. If we take ethanol, ethyl alcohol, we expect it to be soluble in water because they both have OH functionality. They're both polar. We would expect sodium chloride to be dissolved in water or ammonia because they are polar solvents, and sodium chloride is highly ionic. So these are the types of decisions that you have to make. Now, for many people, these are somewhat intuitive now. They've seen it before just through life and through experiences. But the reason for this is because like dissolves like, or like likes like. And so we have the nonpolars will dissolve each other, the polars will dissolve each other, and the ionics will typically dissolve in the polars. Those are some general rules to understand about solubility. Solubility is temperature dependent. Okay? Particularly solubility of a solid. So, both ionic and covalent solids are dissolved in liquids. Generally speaking, that will be the case. Dissolving a solid in a liquid is usually an endothermic process. Basically, that means it absorbs energy. It doesn't give energy off when you take a solid and you dissolve it in a liquid. If you take sugar and you dissolve it in a liquid, it's endothermic. It's more of a cooling effect than a heating effect. Okay? Now, adding heat favors the formation of products then. Okay? Because if you add heat, it drives it to the right side. Because it's an endothermic process. Endothermic process means adding heat favors more of the material being dissolved. So we can dissolve the ions more in a hot solution than in a cold solution, which you intuitively know. Thus, the solubility for most solids tends to increase with temperature. That is a fundamental principle to remember when it comes to solutions and when it comes to making solutions. Dissolving a solid in a liquid at higher temperature tends to favor more material being dissolved than lower temperature. We show you some solubility versus temperature curves for some salts in water. And if you note, each salt has its own unique curve. Some are more soluble and some are less soluble. Some have almost the same solubility at 0 degrees as it does at 100 degrees. For example, sodium bromide is just soluble at a certain concentration almost regardless of what the temperature is. Then you notice some have this really large swing in solubility. For example, potassium nitrate has a really high swing. And then you notice a couple of them actually decrease in terms of solubility with heat. So you want to be aware of that. But the general trend is increased temperature favors increased solubility of a solid solute in a liquid solvent. So how do we describe this thing called solubility? How do we describe the different types of solutions and different types of solubilities that we might encounter? We have 3 terms on this slide that are real helpful towards having a discussion about solubility and understanding the forms of solubility. Here's the first one. A saturated solution contains the maximum amount of a solute that will dissolve in a given solvent at a specific temperature. In other words, saturated solution simply means we put as much solute in the liquid phase as we can. That's it. So we have reached the maximum amount of the solute that we can put in a solvent. And that's called saturation. Okay? Now, the saturation point is dependent upon the temperature. So when we define solubility, we say soluble at this amount. at this temperature. That's a saturation point. Then we can have an unsaturated solution. An unsaturated solution contains less solute than the solvent has the capability to dissolve at a specific temperature. Note the temperature again. In other words, here, unsaturated means it's below what the solvent could accept. So the solvent, so when it's less than the solvent is capable of accepting, that's called unsaturated. And then there's a term called supersaturated solution. A supersaturated solution contains more solute than is present in a saturated solution at a specific temperature. In other words, you've gone overboard. Okay, you've added more than the solvent really wants, and it's called supersaturated. And sometimes solutions will be made supersaturated to ensure that the maximum amount of the solute is in the solution. So once it reaches that saturation point at that temperature, it will not accept anymore. So the supersaturated ensures that you're at the saturation point. So many times people will make a supersaturated solution in order to ensure that the amount of solute is at its saturation point in that solution. Okay? An example would be sodium acetate. Sodium acetate crystals rapidly form when a C crystal is added to a supersaturated solution of sodium acetate. In other words, once you reach that saturation point, adding more will cause some solutes to basically fall out of solution. So the supersaturation point will be when you start to see the solute fall out of solution. That means you pass the saturation point. Okay? So, solubility forms involve saturated solutions, which means you have the optimum amount of solute in solvent. Unsaturated solution means you have less than the solvent could accept. And supersaturated means you pass the ideal saturation point for that solution at that temperature. In these next slides, we're going to show you some formulas for making solutions to help understand the concept of solutions and solute in solvents. We will not be working many problems for this. We will assume that at this point, you are capable of taking these formulas and working through them. Okay? So let's talk through the formulas and what they mean. The first one starts with solubility. Again, solubility is the maximum amount of solute that dissolves in a specific amount of solvent at a temperature. It can be expressed as grams of solute per 100 grams of solvent, usually in water. So when we talk about this solubility and we're using water, solubility in water, it's usually gram per 100. And that simply means percent. So typically solubility is reported as a percent. The number of grams per 100 grams of solvent. And water is a very typical solvent that's reported for a lot of materials. But there are other solvents that it can be reported in. Okay? So that's the formula for solubility. It's basically a straightforward percent formula. Okay? And then we have mass percent. Mass percent is mass over mass. How many grams of the solute over the total number of grams of the solution. And that is based upon a 100 gram solution ratio. Essentially, again, it's mass per 100 grams. It's essentially, again, a percentage. It's using the mass. The key here is to remember your total mass is what you're looking at, and you will then convert that on a per 100 gram basis. So again, it's a straightforward percentage calculation. Similarly, we have mass volume. It's per 100 mils of solution, but this mil solution is different from the grams of solution. Oftentimes, the volume will have to be converted using a density calculation, but you know how to do density calculations. So, basically, the mass volume is mass per milliliter times 100. The mass is mass per 100 gram times 100, which is very much like doing the standard solubility calculation that we showed you on the previous slide. These are not strange formulas to you at this point, so we expect that you can actually handle these types of calculations simply by looking at the formulas. Another way that solutions are described is by their molarity, which is molar concentration or moles per liter. So we have molarity, which is used when working with solutions. The moles of solute per 1 liter of solution. So how many moles of that solute do you have in the liter of solution? And you will use gram per mole or molar mass as a conversion factor oftentimes in these types of calculations. Again, these are calculations by now we expect that you actually can handle simply by looking at the formulas. There are no variables in this that you've not seen at this point in your chemistry studies. Okay? So an example would be, what is the molarity of a 60 gram formulation that has 0.250 liters of sodium hydroxide solution? So we can see the relationships here. Molarity is equal moles per liter. We converted the grams of sodium hydroxide to moles, which is 1.60 moles of sodium hydroxide. Again, a calculation that you are now familiar with carrying out. So we simply divide that through. We just show you how the ratios work out here in the math if you're doing the math without a calculator. And it turns out to be 6 molar. Okay? 6 molar solution. Okay? So this shows you how to do those calculations. Again, calculations that by now we expect that you can actually handle. And then there's molality, which is not molarity. Molality is moles per kilogram of solvent. So molarity, with the R, is the ratio of moles per liter. Molality, with the L, considers the ratio of moles per kilogram of solvent. So molality is used to calculate freezing point lowering and boiling point elevations. So there's certain areas of chemistry where one formula or one type of solution is used over the other. And as you grow in a chemistry career, you know when to use molarity and when to use molality. You also know when to use mass to mass and when to use mass to volume. You also know when to use simple solubility to do it. So these are typical formulas that are involved in studies of solutions in chemistry. Let's talk now about the subject of electrolytes. So what are electrolytes? Substances that dissolve in water and undergo a physical or chemical change to produce ions are electrolytes. In other words, when ions are formed in the solution, in water, we call that an electrolyte. If the solute dissolves and forms ions, it is an electrolyte. That is an electrolyte. You get a positive charge and a negative charge in an electrolyte. Okay? So, when ionic compounds, and we know ionic compounds are those that contain a metal cation and a non-metal anion or a polyatomic anion. Good salts or good ionic compounds are those composed of group 1 and group 2 with elements in group 16 and group 17. So, when an ionic compound dissolves in water which has hydrogen bonds, the ions in the solute separate and disperse uniformly, homogeneously, throughout the solution because water molecules surround and solvate the ions. Solvate, interact with the ions, reducing the strong electrostatic charges between them. In other words, because the compound, the substance, the solute, has dissolved, it is essentially stabilized by the interaction with water. It becomes stabilized in the solution because of its ionic interactions with water. And in those interactions involve the cationic portion of the solute interacting with the oxygen, partial negative charge, and the anionic component of the solute interacting with the hydrogens, the partial positive hydrogens in the water to solvate, surround, and form a solution. We show an example here with potassium chloride. Potassium is located in group 1 and chloride is in group 17. Therefore, it makes a really strong ionic compound. So, as potassium chloride dissolves in water, the ions are hydrated, are solvated. So once they're solvated, they are hydrated. So you'll hear the term solvated and hydrated used interchangeably. The polar water molecules are attracted by the charges on the K plus and the Cl minus ions. Water molecules in front of and behind the ions are shown in this diagram. And we show them in front and behind, but they're really all around it. There's no real front and back in the solution, but we talk about it in that fashion. So essentially what we're saying is that water molecules surround the K plus and water molecules surround the chloride to the level of its saturation. So we get water surrounding the ions to the point of saturation. Once we pass the point of saturation, we simply have KCl floating undissolved in the solution, and that's shown in this diagram where we have the KCl, KCl, KCl all bunched together. That's showing a point where we have now passed saturation to where the sodium chloride is in the water, but it's not dissolved in the water. It is being wet by the water, but not dissolved. In other words, that means that no more potassium and no more chloride is dissolved in the solution. We have reached a point where that's the maximum number of ions the water will accept. So again, substances that dissolve in water and undergo a physical or chemical change are called ions. They produce ions, and therefore they are electrolytes. Electrolytes are ionic species. We can have non-electrolytes. That means that the substances do not produce ions when dissolved in water. So if you put something in water that does not produce an ion, even though you said, boy, it dissolved, yes, it dissolved. The material dissolved, but it did not separate into ionic species. Dissolving in versus separating into ionic species are two different phenomena. Okay? In the ones where it dissolves in but does not separate, you still have the entire molecule floating around, dissolved in the water. In the case where it separates into ions, you don't have the molecule anymore. You have the individual discrete ions. Strong electrolytes dissolve essentially 100%. So you get 100% of the ions, and that's the way it is for strong salts, strong ionic compounds. By the way, the term salt and ionic compounds are used by me interchangeably. Be aware of that. So these strong electrolytes dissolve 100% in the water. That's what they do. And when they do, they produce an electrolyte solution. You can also have weak electrolytes. Only a small amount of the solute will dissolve and form ions. So it may dissolve, but only a small portion of that will become ionic. That's a weak electrolyte. So in a weak electrolyte, essentially when you put that material in, you have fewer ions in the solution. Strong electrolyte, you have a lot of ions in solution. Non-electrolyte, no ions. So non-electrolyte, no ions. Strong electrolyte, many ions. Weak electrolytes, few ions. That's how we differentiate an electrolyte solution. So let me show you some examples of all three. We show you here some strong electrolytes. First set are acids. Strong acids are strong electrolytes. That's the rule. If you know it's a strong acid and there are tables of strong acids, you will learn more about acid-base chemistry in other chemistry courses. But if you know it's a strong acid, assume it's a strong electrolyte. In this case, the positive and negative ions in the molecule completely separate. HCl in water completely separates to give you H plus Cl minus. Now, because the H plus is associated with water, it's called a hydronium ion, which means it has a H3O plus. Okay? So we have the hydronium ion. Likewise with nitric acid, same thing. We get the nitrate and the hydronium ion. Then we go through the other acids. We know the battery acid is sulfuric acid. Okay? So any of the strong acids, you will have this same phenomena. And we write them as AQ because they are completely dissolved as ionic species in water. So what about the basic electrolytes? Same process, except in this case, we form the sodium plus, OH minus. Same principles, same approach. It's in water, completely dissolve the ions, and we have three examples of bases here: a sodium base, a potassium base, and a barium base. Okay, these are hydroxides. So you can assume that if it starts with an H and you know it's a strong acid, it's going to be a strong electrolyte. You can assume if it ends with an OH and it's a strong base, it is going to be a strong electrolyte. Strong electrolytes mean it is completely dissolved in the solvent, in water. And then there are the weak ones. For the weak acids, I find that many freshman chemistry students simply have to memorize them. Okay? So you want to take a look at this list, and if it's not a strong acid, it's probably a weak acid. You get it? Right? So if it's a weak acid, it's a weak electrolyte. By the way, organic acids tend to be weak acids, acetic acid, and other fruit acids, which are carboxylic acids. So here, HF is a weak acid. It doesn't dissolve. And we have the nitrous form acid, HNO2, and that forms a NO2 minus anion instead of nitric acid, which forms a NO3 minus. Watch for that one. And then you have all the others here shown as well. And water, by the way, is a weak acid or actually a weak base. Okay? So it works both ways depending on what the other species is in the phase. Okay? So be aware of that. So we show you the weak ones. Again, weak ones meaning fewer ions. Fewer ions means weaker electrolyte. So what's this electrolyte about anyway? It's about conducting electricity. In order to be an electrolyte, put simply, it conducts electricity. That's what an electrolyte is. So a non-electrolyte will not conduct electricity. A strong electrolyte will conduct electricity really strongly, and a weak electrolyte won't conduct electricity. That is really what an electrolyte is. If it strongly conducts electricity, it is a strong electrolyte. If it weakly conducts electricity, it is a weak electrolyte. And if it does not conduct electricity, it is a non-electrolyte. thus far, we've talked more about solids in liquids, or in some cases, liquids dissolved in liquids. But there are also gases that will be soluble in a phase. So let's talk about the solubility of gases. And this will be a brief discussion about Henry's law. It will be an overview of Henry's law. Okay? And here's how it works. The solubility of a gas in a liquid is proportional to the pressure of the gas over the solution. And that's what Henry's law is. It says that the concentration equals a fudge factor, a constant, times the pressure. And that constant K, that fudge factor, as some might want to refer to it as, or perhaps more properly, a correction factor, times the pressure equals the concentration. That's Henry's law. The solubility of the gas in a liquid is proportional to the pressure. That is the bottom line. As pressure goes up, solubility goes up. As pressure goes down, solubility goes down. So as goes pressure, there goes solubility. You get it? The concentration of the gas in the phase follows pressure. C is the concentration, often molar concentration of the dissolved gas. P is the pressure of the gas over the solution. And K is a constant. It is a correction factor for each gas, and it's typically in moles per liter atmosphere. So therefore you want to have your pressure in atmosphere. But the key is to pay attention to the units in the constant when choosing your pressure. Okay? So the units must match, and you're aware of that by now. So we know then that pressure and concentration of a gas are directly proportional. We also should point out that temperature and concentration of a gas are inversely proportional. In other words, when it comes to dissolving gases in a solvent, temperature goes up, concentration goes down. Temperature goes down, concentration goes up. So be aware of that. So pressure and concentration are directly proportional. Temperature and concentration are inversely proportional. And those are two basic fundamental rules that we expect you to retain when we talk about the solubility of gases. So let's work a problem with Henry's law. The solubility of a nitrogen gas at 25 degrees C and 1 atm is 6.8 times 10 to the minus 4 mole per liter. What is the concentration, the molarity, of nitrogen dissolved in water under atmospheric conditions? Note that the partial pressure of nitrogen gas in the atmosphere is 0.78 atm. And here's the solution. The first step is to calculate K. So we have K available. Once we have K available, we can plug it into the equation and obtain a molarity. So, if we note that C equals Kp, we can put in 6.8 times 10 to the minus 4, because we told you that that was the solubility, and that equals K times 1 atm. We then obtain a value for K of 6.8 times 10 to the minus 4 mole per liter atm. That gives us that value. Now, we will take that K and plug it in to the problem where we have the partial pressure being 0.78 atm. And we put that value in times this K, which is the correction factor. So correction factor times the pressure gives us 5.3 times 10 to the minus 4 mole per liter, which is molar. Okay? So big M equals mole per liter. So note that the decrease in solubility is the result of lowering the pressure from 1 atm to 0.78 atm, and that is an important principle to hold on to. Okay? Let's work another problem, Henry's law. At 20 degrees C, the concentration of dissolved oxygen in water exposed to gaseous oxygen at a partial pressure of 101.3 kilopascals is 1.3 times 10 to the minus 3 moles per liter. Use Henry's law to determine the solubility of oxygen when its partial pressure is 20.7 kilopascals, the approximate pressure of oxygen in the Earth's atmosphere. So, all right, this is a straightforward use Henry's law equation to put in the values. Okay? Now, we know that according to Henry's law, for the ideal solution, the solubility of the gas is given at these values, 1.38 times 10 to the minus 3 moles per liter, or molar. It is directly proportional to the pressure of the undissolved gas above the solution. Basically, we're restating the principles of Henry's law. Now, because both concentration and pressure are known, this relationship can be arranged and used to find K. Again, we're going to find the correction factor, K, the constant. So we have concentration equals K times pressure. We rearrange it and we simply put in the values. Rearrange the equation, put in the values, we solve them through, and we note that our units are proper because they cancel out and give us a value of 1.36 times 10 to the minus 5 for the K value. Now what we're going to do again is take K and find the solubility at the lower pressure. So essentially it's like finding it at a known standard level or known standard concentration, and then put it into an unknown or a new concentration pressure using the K from the standard. So we have C equals Kp. We put in the values now with the correction factor of K of 1.36 times 10 to the minus 5. We put it in, we check our units, we run the units through, and we get an answer of 2.82. Note that various units may be used to express the quantities involved in these types of calculations. Any combination of units that yields the constants and the right dimensional analysis are acceptable. The key is to watch the units, work the units through until you get the proper answer. Now, there is one concept that we must bring to your attention. It is a one-slide definition concept only. That concept is miscibility. Miscibility involves liquid-liquid interactions, and this is an important concept when it comes to making solutions in industry and for many, many applications. And here it is. Some liquids may be mixed in any proportions. In other words, these two liquids, they will mix. Doesn't matter whether one's high, one's low. One can be high today, it can be low tomorrow. Doesn't matter. They're just always mixed in any combination. They're infinitely mutually soluble and are said to be miscible. In other words, whether one's high, one low, it doesn't matter. You can always mix them. Miscible liquids are typically those with very similar polarities. They're so much alike that it doesn't matter how you mix them. Okay? So one's more dominant, so it's the solvent. Tomorrow is less dominant, it's the solute. You get it? If you want to think of it in that fashion, which we do. Get it? So, miscible materials, however, we tend not to talk about them as solute solvent. We tend to simply talk about them as miscible solutions or miscible liquids. Two liquids that do not mix, however, are said to be immiscible. So if they're completely soluble in each other, miscible in each other, we're called miscible. If they're not, they're called immiscible. These separate into layers. So you'll get layers of it. So these two are immiscible. You put them together, don't care what you do, you have to shake them to use them because they're immiscible. Yes, you might use them, but you have to shake them before you use them so that they kind of shake up and they compatibilize and you use them. Okay, so that's immiscible. And then partially miscible. Two liquids that are moderately mutually soluble are said to be partially miscible. The two liquids usually stay together, but if you don't watch it, they'll form two layers. So they're partially miscible. So these materials we don't talk about quite as we do when we talk about the fundamentals of solubility. However, they are mutually soluble in each other. They mutually will dissolve each other, and they're called miscible. So the distinction between immiscible and miscible is really one of the extent. So the miscible liquids are so infinitely soluble, while liquids that are said to be immiscible are lowly soluble. In other words, if it dissolves in each other a lot, then it's said to be highly miscible. If they don't dissolve in each other a lot, it's basically said to be slightly miscible or partially miscible, or in some cases, immiscible. So that's the concept of miscible liquids. They're either miscible, immiscible, or partially miscible. One last topic that we will briefly discuss in this chapter is colloids. And this is a very brief overview of what a colloid is. So, what is a colloid? A colloid, or colloid dispersion, is a mixture in which relatively large, solid, or liquid particles are dispersed uniformly throughout a gas, liquid, or solid. Colloids are not formal solutions. They are dispersions. So instead of viewing it as a solute dissolved in a solvent where there are smaller dimensions of the solute in the solvent phase, what you have for a colloid are larger particles of the molecules dispersed throughout the solvent phase, and in that case it is not a true solution. Okay? Now, when we talk about the dispersed phase is a substance present as relatively large solids or liquid particles in a colloid. So you have the dispersed phase, that's the equivalent of the solute in a solvent solution. So in a colloid, you have the dispersed phase in some type of medium. And that medium is called the dispersion medium. It's a solid, liquid, or gas in which the colloid particles are dispersed. For some, this might sound like splitting hairs, but in terms of how the materials respond in certain application, it is very much dependent on whether it is a true solution or a dispersion. One of the ways to determine whether or not it's a solution or a colloid is by shining a light through the material. If light is scattered, it is a colloid. If it's not, it's a solution. That effect is called the Tyndall effect. The Tyndall effect is light scattering by particles in a colloid or in a very fine suspension. So, if you shine a light through what you think to be a solution or a colloid, the one that scatters light is a colloid. The one that does not scatter light is a solution. And in fact, the size of the particles in some colloids are so large that you just see that you can't see through them. They're translucent or they're cloudy. So let's talk about this a bit further as we compare colloids to suspensions and solutions. Now, a solution is a homogeneous mixture that appears clear, such as salt water in an aquarium. Salt water forms a true solution because the particles are very small, they're down at molecular level, whereby they are intimately surrounded by the water molecules, and there are fewer salt molecules that are attached to each other than they are individual ions surrounded by water. So we have the individual ions in a seawater solution that are completely surrounded by water molecules. So that is a true homogeneous solution. Smaller particles intimately dissolved in a water phase. In a colloid, such as milk, the particles are much larger, but they remain suspended and do not settle. And that is an important principle to remember about colloids. They don't settle. They have particles, and they have large particles, but they do not settle out. That is an important feature of a colloid. A suspension, however, such as milk, is a heterogeneous mixture of a suspended particle that appears cloudy and in which the particles can settle. So mud will settle out. Okay? Colloids don't settle out, and that is an important differentiating feature. So we can differentiate a colloid from a solution by scattering light, because in the solution we have smaller particles of the individual species, for example, ions in the solution. In the case of colloid, we have these larger particles, but those larger particles are completely suspended in the dispersion medium, and they stay suspended, but they scatter light. In the case of a suspension, it too will scatter light, but the particles are larger and they will settle out. So colloids do not settle. They remain suspended in the dispersion medium. So let's show you some examples of colloids. We have an example of smoke and dust. That's a solid in gas. Examples, you have starch in water, some inks, paint, and milk of magnesia. These are sols. They're solids in liquid. Then we have some colored gems, and some alloys are solids in solids. That's a pretty interesting example of a colloid. There are liquids and gas, such as clouds, fog, mist, sprays. We see these all the time. That's why we're able to see them, because the light is scattered. That's why we see the clouds and the fog, the mist and the sprays. Then we can have liquid and liquid, which is milk and mayonnaise, butter, and things of that nature. And then we have liquid solid, jellies, gels, pearls, water in silicon dioxide, which is sand essentially. Then we have gas, liquid, foams, whipped cream, beaten egg white. So these would be examples of colloids. And again, colloids are mixtures in which a relatively large solid or liquid particle is dispersed uniformly throughout a gas, liquid, or solid. Colloids are not formal solutions, they are dispersions. And that is an important principle to remember about colloids. They differ from solutions in that they scatter light. They differ from suspensions in that they don't settle out. And there you have it. Chapter 11, one lecture only on the topic of solutions and colloids.